In this video, we will see how to apply the equivalent lateral force procedure according to UBC 1997. So these are the steps. There are 11 steps to apply. So let's consider the example. This is the drawing given. This is the plan view, and this is the 3D view. So we have also shown you the elevation over here. This elevation is drawn looking at from this side. This is the elevation I'm drawn on the next page. So this is the data you can see. This is a total of 10 stories, and each story height is 12 feet, so a total of 120 feet height. The weights, in real case, you'll have to calculate the weights, but in this case, I've directly given the weights, seismic weight. These are seismic weights, not the self weights, but these are seismic weights for each level. Okay, so for level 1 to 9, it is 1,347 kip, and for the last one, it is 1,298 kip. So seismic weight of the building is 13421. This is the total seismic weight of the building, 13421. The total height of the building, as we discussed, is 120 feet. N means N is the highest number of level, so it is H, and represented by HN, 120 feet. Soil profile type is given to be SC. Location of the building is, let's say it is somewhere in Balakot, and Balakot falls in seismic zone 4. Structural system type is special moment resisting RCC frame. Occupancy category is standard occupancy structure, just normal commercial building. Seismic source type is, let's say, B, and the distance to the source is 15 kilometers. So let's see how to apply step by step. So step number 1 is find the seismic zone factor. Since we know the building will be in Balakot, and Balakot is in the seismic zone 4. So for seismic zone 4, the seismic zone factor Z is 0.4. So let's list it down, Z equal to 0.40, or maybe 0.4. Step number 2 is seismic source type. So again, it is directly given to be B. If it is not directly given, you need to know this data based on which you can decide. For this case, in this example, it is directly given that seismic source type is B. Step number 3 is to find the near source factor NA and NV. So NA, this is the table. So we have the seismic source type B and the closest distance to the known seismic source. In our case, it is 15 kilometers, which is greater than 10 kilometers. So the NA is 1.0. Similarly, for the NV, seismic source type B, and distance is greater than, it is equal to 15 kilometers, so we fall in this case, it is equal to 1.0 again. So both NA and NV are 1.0. Then the next step is to determine the soil profile type. In this case, it is again directly given. We're not given this information. Instead, we're directly given the soil profile type. If you are not given any information regarding the soil type, it's not directly given to you, or it is, this data is also not given to you, so then this code says that you can assume it to be SD, but in our case it is SC. Okay, so what is the next step? You find the ground response coefficient CA and CV. So for CA, we have, so based on the previous steps, soil profile type is SC and seismic zone factor is 4. So if you draw these two lines, you will intersect at this point, 0.40 NA. So CA is 0.40 NA, as you can see over here, and NA was 1.0 from the step number 3. So CA is 0.4. Similarly for CV, it is soil profile type SC with seismic zone 4 with Z equal to 0.4. So this is 0.56 NV. Okay, NV is 1 from step number 3. So CV is also is now 0.56. So CA and CV are now calculated, and then is to find the fundamental period T. It is we are using method A. Method B is a little bit more involved, so we're not using method B. We're using method A, which is simpler. So you just need to know CT and HN. CT depends on the structural type. In our case, it is reinforced concrete moment resistant frame. So we'll take CT equal to 0.030, and HN is the total height of the building, which is 120 feet. So so there you go, T equal to 1.09 second. And then the step number 7 is to find the response modification factor R. So since our system classifies into a moment resistant frame and it's a special moment resistant frame made of concrete, so for this case the R value is 8.5. So you can just list down R equal to 8.5 from this table, and then you go to the next step, step 8, importance factor I. In this case, we are given that it's a standard occupancy structure, it's just a normal commercial building, so I would be, this is the factor you need to look at, this is I, which is 1.0 for our case, so I is equal to 1.00. Sorry. Step number 9 is seismic response coefficient, are also known as seismic base shear coefficient, represented by C with a subscript S. So this is calculated by this formula, CS equal to CVI over RT. Now these 4 parameters will come from the previous steps as we listed down. So CS is equal to 0.0604. Step number 10 is to actually calculate the base shear V. So these are the equations, this is the expression you'll use, and then there are some limits to be checked. So this thing is known as CS, and we have already calculated CS in our previous step. Okay, so we'll just use it in this step. So V is equal to CS times W, and then this is coming from the last step, step number 9. So W, and W is given data. So V is equal to 810.6 kip. Okay, if this is in kip, then V will also be in kip. Now this is the base shear. So this is the total lateral force that the building has to will be subjected to. And just before you go away, you must make sure that this value falls within the limits prescribed here. So the maximum value. So the maximum value is given by this expression, 2.5 times CAI over R times W. So these things again will come from some of the previous steps. You can just insert the values and get 1578.9 kip. So if this value is this is the maximum that you can allow. So if this value, calculated based on this expression, if this were larger than this value, we would have taken it equal to this. So but in this case it doesn't govern you. The value calculated is already less than the maximum. Okay, so this does not govern. Second check is Vmin. Generally Vmin is equal to 0.11 times CAI into W, and these things again coming from the previous steps. So Vmin comes out to be 590.4 kip. Again, it does not govern, because what does it say is that if your value is too small, lesser than this, then you should take this value. But in this case, it doesn't govern. Additional Vmin for zone 4, this is something especially related to zone 4. Since our zone is 4, as we know in the given data, so we will also apply this check. So this is the V minimum especially for zone 4. And you can just again see the factors 0.8 Z NVI over R times W, and these things again come from the previous steps. So 505.3 kip, again it doesn't govern, so V is 810.6 kip. Okay, so base shear is calculated, and then the last step is to find the distribution of those vertical forces, lateral forces. Vertical distribution of the lateral forces, which means we'll have to allocate the some portion of this base shear value, to each level. We have 10 levels. We'll allocate some portion of this to each level. So before you start allocating to the other levels, before you start doing the distribution, you need to do one thing over here, which is calculating the FT. Now, what is this FT? It is the additional force to be applied at the top level. Okay, so ft is 0.07 tv. T is the time period in seconds, and V is the base shear. We just calculated it. 61.8 kip. Okay, so out of this 810.6 kip, okay, which was the total base shear, this 61.8 kip will be acting at the top, and there will be some additional forces at the top, just like at other levels, but at the top level this will be additional force. We'll see how we incorporate this. Okay, so another check on, before you just finally say this is 61, ft is 61.8, you should first check if it is the maximum value for ft is 0.25 times the base shear, which is 202.7 kip. It doesn't govern me, which means this check means that if this value happens to be too large, so and even larger than this, then you should take it equal to this. Okay, but in this case it is not too big. It is less than the maximum, so it is okay. This doesn't govern, the maximum value doesn't govern. Now V minus ft is 748.8 kip. Now this is the force that you need to distribute between all the 10 levels, and at the 10th level you will add this ft. Okay, so so let me show you how this works. So you better make a table, because this is how the distribution looks like. So list down the levels, level 1 up to 10, and then write down the weight for each level, and then the height, shouldn't say height, the elevation for each level. So 12, 24, 36, it means for each level it is the elevation from the base. Okay, so it's not the story height. Okay, it's the elevation from the base, 12 up to 120 for the last one. And then you do this product, this column. So 1347 multiplied by 12, you get this. Similarly, 1347 multiplied by 24, you get this, and so on. Okay, and then for this column, WIHI, you just make the sum at the end of all entries in this column. Okay, so that happens to be 883140. Now you're ready to start calculating this last column. So the calculations will look like this. So let me show you how this 13.7 is calculated. So these are the steps. I've shown it for one, and the rest you can understand. So fx, this is represented by fx, and for the first level we would call it fn. So instead of x, now we are saying specific level 1, and equal to v minus ft. This is what we're talking about. So w1h1, okay, generally formula is wxhx. So for the first level it is w1hn h1, and then this is the thing you have already calculated. So these two things will be constant every time you go down the table, but this thing will have to be picked from for each level. Okay, so 13.7 kip is calculated in this way. So this is how you can just do the calculation. Well, if the elevations are just like this, 12, 24, 36, increasing linearly, then you can even do something over here. Just keep on doubling this, tripling, and then 4 times, 5 times, and then, but anyways, this is how you calculate it. And then for the 10th level, you will get 132.1. But then the code says that for the 10th level, you have to add this FT, 193.9 kip. Okay, so for the 10th level, the final value is 193.9 kip. Okay, so now this is the graphical way of showing that distribution. For the first level, it was 13.7 kip, second level, third, fourth, and then this was the 9th level, and then this is for the 10th level. See, it is the linear distribution with respect to the height I'm sorry, up to this story number 9, level number 9, but then for the last story, last level, it is not linearly. It doesn't go linear because there is an additional FT that is added up. So this is how the distribution is done. So this is it for this example.